All right, so thanks, Sylvia. First of all, let me thank the organizers for inviting me to speak and giving me this opportunity to tell you about my work. And today I'll be talking about something that I've been working on for the last year, well, no, half a year, so not that much, with Alexander Homrich, who's sitting back there in the audience. And what we've been doing is setting up the bootstrap for open flux tips. And it's a story that we're very excited about, not just because we bootstrap and we like them and getting bounds of things, but because this system had some very nice surprises that I'm going to tell you about. In particular, at risk of spoiling my talk, we'll see that it opens the door to inputting asymptotic freedom into the flux loop, which is something that many people have been thinking about for a while. Now, you'll notice that there's this preposition in my talk that says towards, which means that we're not quite there. We haven't fully finish up this line of research. So this is very much a work in progress. So we welcome any comments, criticism, and suggestions. Okay, so let's get into it. I'll start by giving the motivation that got us into thinking about this, and then we'll jump into nicer, well, more exciting things as we go. So okay, this is something that I don't need to spend any time on. That's we're interested in this. Everyone in this room in confining gauge theories, and for concreteness, we'll be thinking about pure Yang-Mills in 2 dimensions. And we know that this is a theory that has flux tubes, right? And for a very long radii, for very long flux tubes, these are described as some effective string theory, which has some universal P's and ambiguity, and then some corrections that depend on some Wilson coefficients, right? Now, these Wilson coefficients appear in various observables of the theory. For example, we can compute the ground state energy of a closed flux tube, and it has some universal P's and then some corrections in 1 over the radius with some powers that depend on these Wilson coefficients. Okay. So what that means is that you can measure some of these observables in the lattice, for example, like this plot here, and then you can try to extract these coefficients by fitting this data to the observable. And you can do this in very different ways. There are various observables that capture these Wilson coefficients. Okay. So this is the story about this effective string theory, but that's not the whole story, because this only describes closed strings, closed flux tubes. Okay. But if you're interested in pure Yang-Mills, there's another object that you can put into correlators, which are Wilson lines or probe quarks. Okay? And as soon as you have probe quarks into the theory, you're gonna this will provide endpoints. These are non-dynamical, so this is something that you choose and you pin down. You put into the system and you control them. But nevertheless, they're going to create open flux tubes that will go flow from one port to the other. As you let this flow over time, it'll sweep some world sheet, and will be bounded by Wilson lines, which are just the world lines of this port. Okay? So the point is that if you want to study correlations in pure Yang-Mills, you want to study correlation functions of Wilson lines, you better understand how to. So if you want to describe that from a world perspective, you need to understand open strings. Okay, so that can also be approached from the point of view of effective string theory by adding some boundary effective action. Okay, so we have a bullet action, that's the one that I wrote or sketched before, that describes the interactions in the bullet. But now at the boundary, we can also write down an effective field theory, much like in Char's talk before. But then this was not now for the spinning string, where at this stage we're only caring about the static string. So this one's not rotating. And this introduces some, so there's this boundary action also has an expansion in derivatives with some new and fixed coefficient. The notation is gamma for the ones in the bullet, is the gamma got here, and B for the Wilson coefficients on the bottom. Okay, and this coefficients also coupled to other observables. In particular, you can consider now for example, the ground state energy of an open string. So some string where you have the 2 probe quarks separated by some distance r, again has some universal P's and then some corrections. And this one receives corrections from both the bullet and from the boundary Wilson coefficients. And one important point is that the boundary Wilson coefficients actually appear at orders like several orders before the bulk corrections. Okay, so if you care to measure these observables that have some boundaries, you better understand these Wilson coefficients from this effective action on the boundary. Okay. Now, again, you can measure this observable in the lattice and match this expansion to that. which means that you can also, just like you could obtain the values for these Wilson coefficients in the bulk, you can also do that for the ones in the boundary. Yeah. Yes. Yeah. Well, this would be the.
Yeah.
Oh, yeah. Okay, that's a good point. Yeah. Okay. Yeah. This is yes. There might be a correction from the yes. I removed this guy. Yeah. I'm checking. I guess yeah. I'm using the convention such that r going to infinity. This goes to just the bulk. Well, yes, exactly. So it's a constant. Good. Okay. So these have been measured, in particular in this paper by Brandt in 2018. And this is one example where we computed it for 3D SU and Young various values of NC, the number of colors, and you see it doesn't change much. But in particular, it's always it always has the same sign, so it's always negative. Okay? So looking into this led to the question whether this coefficient in particular was negative because it had to be, or just was a coincidence. Okay? So we know from the bulk whenever we have an EFT, we know that there's many instances that some Wilson coefficients have a definite sign, and that's a consequence of constraints from unitarity and so on. The question is a similar thing going on here or not? So what we set out to do with Alexandra was to try to put bootstrap bounds on these boundary Wilson coefficients. Okay, so that's what we started thinking about. But as you'll see as I go along to try to motivate how one can approach this problem, we'll see that we end up with a system that opens the door to inputting asymptotic freedom into the bootstrap. And if you wish, that's if you don't care so much about the value of this Wilson coefficient, which is fair, this is something that you should take away from this talk. It's something that people have been thinking about for a long time. It's not completely settled now yet, but it's at least some progress towards in that direction. Okay, very good. So I hope I've caught your attention. This is a bit a quick outline of my talk. I'll quickly review how one can do S-matrix bootstrap for flux tubes, and then we'll try to follow the same steps for the boundary Wilson coefficients. So this was done for the bulk, and now we'll do it for the boundary. We'll see we need a new object called the R matrix, and we'll list the consistency conditions, which will lead to a new constraint for this R matrix, which is the one that will link to asymptotic freedom, as we'll see. Okay. Good. So very quickly, a review on the S matrix bootstrap for flux tips. This was pioneered in this paper up here in 2019, and the idea is very simple. So once you understand that you have this confining string that is described by some EFT, and you go to a bootstrap person and you tell him or them that you have some Wilson coefficients, then the immediate thing to do is to translate it into an S matrix. So that action can describe some scattering of some degrees of freedom in the worksheet. In this case, this Goldstone transverse excitations. And then the effective string theory will describe the low energy expansion of this S matrix. In particular, here you find that the S matrix are 52 Goldstones, and this would be for d equals to 3, but you can do this in more general dimensions. So indeed, low energies, it means an expansion in terms of these Wilson coefficients. There's a universal non-Goldstone term, and then a bunch of correction. Okay. Now, since this S matrix has to satisfy some conditions, you can translate those into bounds on these Wilson coefficients, and that's the essence of the bootstrap. So one has to do is list the constraints that the S matrix satisfies, and then try to convert those constraints into bounds for these Wilson coefficients. Now, what are these constraints? Well, we know that it's first of all analytic in the energy plane, and except for some cuts on the real axis that correspond to the S channel cut and the T channel cut. Then there's crossing that links one to the other by analytic continuation, and moreover, there's unitarity, which bounds the absolute value of the F matrix along the real line. Now, since this is a function, so this is an analytic function that's bounded on this boundary, you can the function is not allowed to do anything it wants in the bulk. Now you can play some systematic games, either analytically or numerically, to translate these constraints on the S matrix everywhere here into bounds on these Wilson coefficients. So I won't get into the details of how that's done, but I'm gonna just copy the results here from this paper. So the bounds were first derived in this paper, but here they nicely contrasted it with data. And you see that the bootstrap bounds tell you have to be above this orange curve. And indeed, the lattice points agree with that. So the goal is to try to repeat the same thing, but for the boundary coefficient. Now, the first thing we need to do is understand what's the observable that captures the boundary Wilson coefficients. And that's the R matrix. So instead of the S matrix scattering things in the bulk of the string, we're now going to send goldstones against the boundary and have them reflect back. Okay, so we define this R matrix very similar to the S matrix, but with incoming flux space states in the presence of the boundary. The one-to-one process of this thing going to the boundary. Now, this has been discussed a lot and studied in the context of integrability, following the work, the seminal paper by Yoshel and Samologico, but this can be defined beyond integrability. And now the key point is that at low energies, the boundary Wilson coefficients appear in these R matrices, and they do so in the following form. Okay, so at low energies, there's the first contribution that essentially comes from the non-Bogota term. If you wish, you can integrate by parts, and that gives the boundary term. And then there's intrinsic Wilson coefficients from the boundary, these P2 and P3 and so on. But then it also receives corrections from the bulk corrections from the bulk Wilson coefficients itself. So there's this whole array of Wilson coefficients from bulk and boundary. And now notice that the expansion is not in S, but in P, because we've broken Lorentz symmetry. Okay. Now, what we want to do, since we have this object, now what we want to do is bootstrap and try to see what are the constraints that this object should satisfy, and translate those into bounds for these Wilson coefficients. So let's follow our nose. The first thing is an analyticity for this R matrix. And R, by the way, stands for reflection, in case I didn't say that. Because it literally reflects. Good. So the first thing is analyticity, and that just much like in the S matrix, we have an S channel and a T channel that now look like I've rotated by 90 degrees because I'm plotting P instead of P squared. That's S, but it's the same thing. So we have analyticity everywhere except for this cut here and that cut there that correspond to S channel and T channel exchanges that look something like this. This would be the kind of diagrams that would contribute singularities here and there. Okay. Now the next one was crossing symmetry, and crossing symmetry here is a bit different. So crossing symmetry is still the same, that I can link from the S channel to the T channel by analytic continuation, but now we need to understand what's this T channel here. And this T channel corresponds to rotating our head in this picture. So the R matrix was defined, if you wish, as time flowing upwards, where we have one particle state coming to the boundary and then we're going back. But now we can rotate the time direction and look in this direction. Now we have a boundary state in the bulk Hilbert space emitting two particle states going left and right in the bulk Fock space. Okay. So we have this other process, and crossing is the statement that this matrix that I defined K, that this was R in this S channel and K in this other channel. The crossing is just a statement that K is the analytic continuation of R. Okay. Good. So we're almost done. Now the next thing that we need, if you recall, was boundedness of the S matrix on this red line. Now. Here, we need to deal with each case separately. The first one is the S channel, and here it's still bounded by 1. And the reason is that we still have an incoming state going to an outgoing state that looks, so the incoming state and the outgoing state is the same, and we can follow the same logic as with the S matrix to see it's bounded by 1. But if you want to apply the same logic in the T channel, you cannot, because the incoming state is different from the outgoing state. So you need to be a little more clever. This is not just going to be bounded by 1. And you may ask, well, do you really need this? Isn't it enough to have this bound, to put some bounds on Wilson coefficients? And the answer is no, because you have an analytic function that's allowed to do, so it's bounded here by 1, but it's allowed to do anything here, in particular along the boundary. So this is still it has too much freedom, and it allows for B2 in particular to be anything. So we set up this numerically, and we see indeed that there's no bound in B2. So we really need to push through to try to get an upper bound on the absolute value of the K matrix along this line. Okay, so that's the question. What is the unitarity matrix? What's the unitarity condition along this K matrix line? Good. So what can we do? So we can draw some inspiration from the form factor bootstrap that I'm sure we'll hear a lot about in the next talk by Martin. What is the form factor? It's a very similar object, but now we have a local operator emitting, in this case, 2 particles into the bulk. Okay. Now, this defines similar to the K matrix, something called F, that's the form factor, and the question is the same. Can you obtain some unitarity? What's the unitarity constraint on the form factor? And this was understood in this paper by Penedon, Scarlett, and Kuhn in 2019. And the insight of that paper is to realize that you can obtain a unitarity bound for this by putting it inside a matrix of inner products. Okay, so right, so you take a matrix of inner products where you have the local operator in momentum space and the flux space states, and in the off diagonals you have the form factor, modulus and delta functions that I'm removing. Here you just have a delta function from the inner product of flux space state, and up here you have the 2-point function of these operators. So what you get once you Fourier transform is the spectral density in this entry, which is just a count of the states that couple to the point operators. So since this matrix has to be positive semi-definite, in particular the determinant has to be positive, and you find that the form factor squared is bounded by the spectral density. Okay, and this is what's the answer to what's the unitarity condition in form factor. So we can try to follow the same logic and apply the same strategy to the boundary to the K matrix. So what does this look like? Well, I just replaced the local operator by a boundary at some given energy, and indeed I'll have in the off diagonal the K matrix and K star. This is just some kinematics from the flux space states, and then here I have the 2-point function of boundaries, Fourier transforms to energy and momentum space. Now this is again a spectral density, and it may look a bit weird at first, but it's not. It shouldn't be too strange, because this is a spectral density that appears in the partition function. Because what are we doing here? We're taking the inner product of a boundary state to another boundary state. And then instead of talking about some time translated between one to the other, we're talking about energies. So what this defines, if you do it in position space, is just the partition function, the cylinder partition function with the 2 boundary conditions at either end, right? And then if you write this in energy, you see that this is where the spectral density is encoded. Okay, so we've answered our question. We have an upper bound on the K matrix from this determinant in terms of the spectral density. So we'll put a hold on this, and we'll come back to this constraint in a second. I'll try to, we'll see the implications of this. But first, I want to explain that this spectral density, apart from having an interpretation from the worldsheet, because recall, everything I said here was 2D. We were always on the worldsheet of this flux tube. But this also has it features in some object from spacetime. Okay, so recall, we're doing 3D Yang-Mills or whatever dimension Yang-Mills, and we have some flux tubes, and now we were on the flux tube. Now we're going to jump off the flux tube and talk about spacetime. So where does this object feature there? This happens in the string propagator. So what is the string propagator? This I define as the following. I take the time order 2-point function of Wilson loops, okay, here and there, and then I Fourier transform along the time direction. I take these loops to be parallel. Right? Now, so what's the picture that you should have in mind? You have a Wilson loop that acts at time 0. It creates a string, and that propagates for some time, and then I kill it by another Wilson loop. Okay? And then I Fourier transform, and this defines what I call a propagator. Now, this is a little tricky how to define it, and you need to be careful and define it through analytic continuation to patches and so on. And once the dust settles and you understand all that, you see that this propagator, much like you would get in the propagator for particles, is analytic in the energy plane, except for the real s-axis, where it has an imaginary part that's exactly the spectral density that we discussed before. Why? Because, well, this is just counting the string states that propagate from one to the other. Okay. So if this sounds a bit too unfamiliar, what you can do is go ahead and compute it in critical string theory, just to get a handle of this and see an example of how it works out. And okay, so there, what's the picture? We're critical bosonic string theory in 26 dimensions. And instead of Wilson lines, now I take D branes. I take a D brane, it creates a string, propagates for some time, and then I kill it again, and Fourier transform. So the first thing is compute this guy here, and that's essentially the cylinder partition function with Dirichlet boundary conditions along the transverse directions of the branes. So this looks like this: a textbook exercise, have the oscillators, the Dirichlet directions, Neumann directions, and an integral over moduli space that you need to be actually careful how to do it. You need some funny contours on you need to regulate the contours in order to get something meaningful here. But that's essentially the object. And now what you are instructed to do is take the Fourier transform and look at what it looks like in complex plane. So once you do the Fourier transform, it reduces to this, which is essentially, probably speaking, the Laplace transform of a modular discriminant. And then you can expand here. There's some expansion at low energies at a small tau, and you see that this can be expanded as a sum of poles. And what are these poles in S? Well, you see that it's literally the closed string spectrum, right? So here I find the tachyon pole, the graviton pole, the first massive string mode, and so on and so forth. So I find that indeed, in critical string theory, I find that it's an analytic function everywhere except for a bunch of poles which correspond to the closed string, right? Okay, so now that we've understood that the spectral density is a very meaningful object, we can go back to the bound and understand the implications. Okay, so recall this is the bound we found, but the K matrix, which is what we needed for bootstrap, is bounded by the spectral density. Now, in order to understand this bound a bit better, what I can do is I can integrate in energies so that I compute the partition functions. There's just integral over energies of this thing, and I do the same integral on the right-hand side. So I haven't done much, I've just integrated. And now you see that things start to look a bit funny, because in order to talk about the K matrix, I need the Hilbert space of a circle that has infinite radius. I need to be at infinite volume if I want to talk about Fock space states. So what I really should think of this is as the partition function, indeed, of boundary and boundary separated by some time tau, but where the length of the radius of the cylinder goes to infinity. And that's essentially infinity. Why? Because you can go to the open string picture, and now you have very low temperature, so only the ground state propagates. And you see that this thing is the exponential minus L. L is this length of the ground state of the open string channel. And this is negative for finite tau. So this thing blows up. And now this bound is essentially trivial. We found that infinity, so that K squared is bounded by infinity. Okay, so that's not good. We cannot bootstrap with that. So what you need to do is try to look for an updated version of this bound that remains finite at large L. And the best candidate is this one, where instead of the spectra of the partition function, you directly have the free energy, which is the log of the partition function at large L. Now, this may look a bit ad hoc, but there's some motivation why we think this is a good candidate, and it's the following. So we can start with a diagrammatic expansion or representation for the spectral density. We have the two boundaries, and we consider at infinite volume, we consider all the Fock space states propagating in between. So you have some expansion that looks like this, and you can start tracking which of these, like what's the dependence on L of each of these diagrams. And you see the first one, so each blob, if you wish, is translation invariant, so it'll be proportional to a factor of L. So this is proportional to L, this is proportional to L squared, and so on. So if you're careful, you'll see that all the connected diagrams are proportional to L. They're the extensive part, and everything else just amounts to the exponentiation of the connected diagrams. So what you should do is you should restrict your sum to connected diagrams, and that's literally the same as log z. Okay, so log z now it means this, where I'm only including connected diagrams. And now this is much better because I have something that's proportional to L, not exponentially now. And it hints that we're making progress. And on the left-hand side, I already have what I want, which is the log of this partition function at large L. And on the right-hand side, I see that the first contribution is the right-hand side of this bound, right? Because I have two particle states propagating, created by K and absorbed by K space tau. Okay? Now the question is whether this is positive. And in general, it doesn't look like so, but we conjecture that it is, because we've checked in many examples, and now I don't have time to get into the details, but we've proven in some cases that this is positive, and we're working on a general proof. But for now, we've checked in many examples some examples that this is true, and we conjecture that this bound is true. So just so that I think, images sell more than words. We can check this bound. This is the conjecture bound. Yes. No, in the cases we've checked, it's term by term positive. In general, it doesn't look like it should be, but for example, in TBA, you see that the measure is positive by causality implies that the measure is positive. So it's very non-trivial to see, but every time we've challenged it, it seems to pass the checks. So we're still working on a general proof, but it looks like actually each term will be positive. I mean, this is a simplified diagram. There's more diagrams than the ones I've drawn here, but this is only like in the free theory case. But we can talk more about it. So yeah, just as an example, we can compute this in TBA in the critical string where we have this S matrix and the related R matrix is this one. And you see the left-hand side is this curve. That's just a GGRT formula. And the bottom line, so the right-hand side is this line. And you see it's indeed bounded everywhere in tau in this plot. And then another example that we checked is this one, which is a CDD flow, also an integrable case, where there's this S matrix obtained by Zaplogikov. And these are matrices that we cooked up so that it's an integrable boundary for this. And again, you solve these blue dots are the TBA result for the left-hand side, and the right-hand side is again bounded by this. Okay, so the jury's still out on this bound. We're working on trying to prove it, but it looks at least these are very non-trivial evidence towards in favor of this conjecture. So what I want to discuss very quickly is why this is an extremely interesting result. And that's because it opens the appearance of this object, the free energy, opens the door to asymptotic freedom. So I'll do that very quickly. Why is that? Well, because it's the energy of an open string, right? And from space-time, this open string is the flux between two probe quarks. And now we're studying this in the limit when, now I can study this in the limit where tau goes to 0, and that's very short distances, where asymptotic freedom kicks in. Okay, so this will essentially be the Coulomb potential. Now I need to skip over this, but you can ask me that there's a subtlety that this does not only receive finite n. It doesn't only receive contributions from the string. It also receives contributions from glue balls. But you can see that this contribution is positive. So essentially, this result, which is the Coulomb potential, upper bounds the energy of the string. Or you can think about large n, and then there only is one string. So what we learn from our bound, so what we see is that the Coulomb potential, which is what you obtain from asymptotic freedom in the regime where tau goes to 0, upper bounds the ground state energy in the open string channel. And now our conjecture unitarity bound is this one. So we learn that this integral is upper bounded by this log, which is, oh, by the way, here I'm showing it for t equals 3, where Coulomb potential is just logarithmic. And now the question is, what do we learn from here? We're learning that some funny integral of k from 0 to infinity in energy is bounded by this thing. Well, what you need to notice first is that this and the small tau, so this should be understood in the tau going to 0 limit. And the tau going to 0 limit of this integral is dominated by large energy. So you can relate this bound into an asymptotic bound on k squared. And you do this by looking what you can put here in order to reproduce the log, and you see that this thing is bounded by 1 over p. So we learned that if using the conjecture unitarity bound and assuming that the theory is asymptotically free in p equals 3 dimensions, p equals 3, you find that the K matrix cannot be constant. It must decay asymptotically. And the very nice thing of this is that it immediately rules out the critical string theory result. I mean, critical string theory is okay. We're not expecting it to be a p equals 3 confinement theory, but you could have asked, well, can I still use this? Could it be that in pure angles this is still the boundary theory? And the answer is no, because if this is a pure phase, then this will not decay asymptotically. And I'm already in negative time, so let me finish. The very quick summary of what I've told you is that we are looking at the boundary bootstrap, which led us to these R and K matrices. We needed a unitarity matrix, a unitarity bound for K that came from this sort of matrices, and that led us to this conjecture, which I have some evidence, significant evidence for that upper bounds the K matrix. And then I told you that this rules out some critical string theory result, but there's much more that you can do with that. And I'll do this very quickly. You can put boundaries. So now that we have this, we can go back and run the boundary bootstrap, which is what we wanted to do. But I want to emphasize that this is not just something about the boundary Wilson coefficients. And that's because this kind of matrices extend to the S matrix. So these bounds will propagate back to the S matrix. So there's hope that by running the boundary bootstrap, you'll improve upon the bounds that we obtained from the people obtained from the ball bootstrap. And that's, for example, one thing that we're imposing now is RK crossing of these two matrices, which, if you recall, was a way to impose open-closed duality for all energies. Okay, so there's hope that this will propagate back will improve the bounds on the gamma 3s, which is what most people, the first thing you would care about. But then, moreover, as I mentioned, this is a door to inputting asymptotic freedom, and we believe this is a very nice result, because most of the time when we do bootstrap or we think about fluxes, we cannot really tell that we care about theories that are that describe asymptotically free theories in the bulk. And now this is at least one way to go in that direction. And the very last point before Sylvia kills me is that this opens up many possibilities, and one very interesting game that could be played is to input these left-hand side values for the left-hand side here from the lattice. So why is this significant? Well, because this is this is an observable that can be measured directly on the lattice. So we could input lattice data into the bootstrap, not by making some fits on some observables, extracting gamma 3 and then inputting gamma 3, which involves many steps, but by directly obtaining this result from the lattice and inputting it in this constraint into the bootstrap. And for all I know, this could be a very good way to obtain from lattice the best fits or the best results for the gammas and the b's of the Wilson coefficients. So we don't know, but this certainly, I think it's a game that's certainly worth playing. And I'll just leave up with where we are right now. And I'll thank you so much for your attention. Sorry for going over time, and stay tuned for updates. Thank you.
any chance of getting non-invertible symmetry to the ED gradient of this one?
Non-invertible symmetry. Yeah, I mean, I guess there can.
The reason I'm asking is that it's just a paper that's not the, it's still not invertible symmetry, the possibility.
Ah, it's a very good point.
And then I don't know ahead of time. Paper.
Yeah, no, so yes, we at least know that, so those are for particles with flavor, if you recall, so like those like are in, when the particles themselves are attached to like some domain wall, like are domain lockings in between some domain, and domain walls between different backbone, and then those carry some labels, and you need to be careful about the quantum dimensions of the topological lines attached to those particles. So we do know, we know that our resultants are not attached to any lines, so crossing will not be modified for our theory. There might still be some selection rules that come from general non-invertible symmetries that I don't know. I haven't thought about that, but certainly, yeah, it's a very interesting question. Thank you for bringing that up, but it does not affect our. Once you take the larger limit, yeah.
You take the last color,
Oh, okay, that's a good point. Yeah, there's a coefficient that is writing Z of n, and saying this coefficient blows up. Right, but are you sure that this energy does not blow up in the same way, large n? Right, because these some diagram, this partition function will be some diagram that also has some n factor. So yeah, okay, it's a good question. I need to I think to think about it. But yeah, but the point is, yeah, okay, it's a good point. But a finite n, this is still an upper bound. So this would be an equality sign at large n, and you're saying this should be infinity on the left. But at finite n, this is an inequality, and this is fine. Thanks for bringing that up.
Thank you, John, again.
Thank you.